Okay.
Cool. Let's go ahead and hop into this. So, start recording. This is our second and last day in chapter 8. This is definitely the shortest chapter of our. That's what we'll be doing, but doesn't necessarily mean it's the easiest. It is the shortest. And we're going to be talking about today. We're going to be talking about just applications in general. So this is just going to be very application based today. Just to think about different ways we can use integration to more expand our knowledge. I mean, we've already applied it in terms of in the past we've done volumes and work, and we just did length yesterday, and we did surface area yesterday, but now we're going to extend that even farther to more physics-based and engineering-based applications, along with some economics and biology applications in the second half. So. Yeah, we will get there in due time, but we're going to start out with chapter 8.3, which is applications of physics and engineering. Okay, so this chapter, again, since it's just like applications, it doesn't really take much time to, here's kind of a setup for the subject we're doing, and that's the arc length and surface area. It's just, here's this thing, here's this thing, here's this thing, that are all maybe kind of related, but really not at the same time, but are all built kind of the same way. And the first one that we learned how to do, maybe I'll go ahead and write the name up here as well, is okay. I wrote these equations up here just to go ahead and have the numbers for everybody to get to that point. But, hydrostatic pressure. So whenever we take an object, right, and we put it into water, or put it in any liquid, really, the water is just going to be a little more cold now to make things easier for us. The farther we push it down, the more pressure that's going to be acting on top of it, right? The more, because water does have, even, it's a liquid, so it does have some sort of weight. So if you continue to move downwards, there's more on top of you, so the pressure just continues to build, right? And so our goal is maybe to understand, if I take an object and put it in water of a certain depth, to understand what the force is that's acting on that plate or acting on that surface that's in the water. And define force, in this case, right, we're talking about a weight being applied. So we're going to take the mass of the object times the gravitational constant. Okay. And although when it comes to finding the mass of that object, right, we need to be cautious, right? You're not generally going to be just given a number. You may be given we need to understand what the area is exactly this is going to be applied on in order to know what the total mass is going to be here. And the way that we calculate this, so the G here just kind of stays, but to find the mass, what we do is we take the density of whatever of the water in this case, and we're going to multiply that by the area that's the surface is taking up in the water, and we multiply that by the depth of that object, right? Because it's going to have the same area always as you move down, right? But how deep you go does also affect how great it's going to be, right? So the deeper you're in the water, the greater your force is going to be, right? And so the pressure here as well is this rho GD is our pressure. So that's kind of where the hydrostatic pressure part comes in, where we have to find the area and just multiply it by this P by this pressure. But this is going to be, finding this force is ultimately what we're going to be calculating here, right? So to demonstrate this process, I have a couple of examples, right? And so we're going to work through these examples, and we're going to kind of figure out what's going on, right? So first, whenever I find the force, I need to find I should be given rho G, and I should be given this kind of delta value, which I wrote here. Generally, when we talk about delta, we're just talking about our SI units. They take the density of the object and they take the gravitational constant and kind of put it together into just 62.5. But if you're talking about metric units, then you need to remember that the density of water is 1,000. And then the gravitational constant is generally actually like 9.8. I know Dr. Watt usually taught his students just use 10, and for the sake of our calculations, it's going to be 10, right? Because you don't want to have to calculate, you have to do 9.8 on a test or something. We don't have a calculator. So that's kind of what we're kind of going to settle with as we kind of work through these, even if it's not accurate, but just helps when we don't have a calculator. Okay, it's close enough. Okay, so rho and g, all that to say, rho g or the delta are going to be set for us. Now, the only things that are going to change are the depth and the area, right? Depending. The depth won't be too hard to find. We just kind of have to, right? We understand, well, where's the surface of the water, right? At, which in this case, it's maybe I'll put a little curvy line so we know where it is in these cases. That's going to be here, right? And so, you know, the depth at this point is 2, for example. The depth down here would be 2 plus 5, which is 7, right? And so we just have to set up some sort of simple linear relationship to know how deep we're going to be. The area is going to be where the area is going to be where things get a little more complicated, right? We're really going to have to think through this, right? The way that we find the area, right, that we're working on the object is I take a look at it, and just like when we find the area of, or like when we're working with area in finding integrals, find the area underneath the curve, we're going to break this object up into little rectangles, okay? Right, because I want to just see what the area of this rectangle is, and then I'm just going to add up all those rectangles, right? Which is obviously, that's where the integral is going to come at, right? When we add up all of these rectangles together, we're going to form the integral of it, right? Each of these rectangles is going to have a particular width, which we'll call, which is going to be our kind of our delta x in this case, right? So that's more broad. Obviously, when we go into the integral, it's going to be dx instead. But it's going to be delta x is the width. So our goal in most of these problems is to figure out what the width is in each case, right? We need to figure out, depending on what the object is, right? Here, you know, we have a triangle. Here we have half of a, this is supposed to be a semicircle. We need to understand how the length of this rectangle changes as we move up and down, okay? So the first thing we want to do when we're dealing with these types of problems, right? So I want to understand what the force is on this object, right? So the first step that we take when we do a problem like this is we need to define where our origin's at, okay? So I want to define where my 0 point's going to be, right? And then everything's going to build from there. You could put your 0 point at the bottom of this thing, or you could put it at the bottom of the object. Typically, the safest spot to put it though is going to be kind of right here at the top of the water, right? So the water is kind of your starting point, right? And then normally we like to have the axis go up, but since we're worried about kind of going deeper, what happens when we go deeper? I'm actually going to have my positive axis go downwards, sort of like this, okay? And just so we can keep using x, I'm gonna do x in this direction. Again, you could always do delta y or y if that's easier to think about, but it doesn't matter because these are just dummy variables at the end of the day for this problem. Good. So what this means for me, right, is that if I go down this distance from the surface of the water, right, then that distance is going to be represented by x. Okay. Now that could be here, here, it could be to the rectangle, wherever it is, but that's going to be my x distance. Okay. So my goal right now is to figure out, right? Maybe I'll leave it on here, kind of fix it so we can see in particular. When my x goes down to the rectangle, when I'm this deep in the water, how long is my shape going to be at that point, right? Because I need to figure out if I'm this deep, this is how much I have of the rectangle in that direction, right? Because if to find the area, I need the length times the width, but I only have the width right now, so I need to find the length. Okay, so to find the length of this rectangle, right? What might be the easiest thing to do is try to see if I can find a way to maybe represent this line here as some sort of equation, right? So essentially, to kind of understand, you know, how the x changes as I move downwards, right? So, so let's think about that. Is there a way that I could look at this line and figure out what the slope is going to be of that triangle? What do we think? What is it? Well, we're not concerned about getting the length of the hypotenuse, right? I'm concerned about I want the slope of this line. Yeah, absolutely. So we have a triangle, which is 5/10, right? So what's going to happen is the slope of this line is going to be, I do 5/10, right? We do the up and down over the, right. Let's see. I got just go through x down. Just trying to hold on. I don't want to confuse them right here, but this is going to be. So typically, right, this equation we would have is going to be, we want, now I'm just going to write this so we think through it, but we want, it's going to be negative 5/10 x, right? Which is going to be negative 1/2 x, right? Now that's, again, that's if, when we draw the graph typically, that would be negative 1/2 x at each spot, right? But which is going to help me a little bit, but I still need to figure out, you know, what exactly this length is going to be if we don't want it to be negative. So let's work from here. Let's see. So we start at 10, right? And then we're going to decrease at a rate of, actually, I think this would. What is it? Right. I think what I might do is maybe instead of looking at it from this direction, maybe we can think about it this way, right? So I'll call, just to give this direction a name, I'll call this y, right? Or sorry, not that direction, this one. Call this left and right direction y. And so the equation that we actually want, right, given how far we go down in the x direction, is going to be y equals should be 2x in that case. Because what's going to happen is I'm going to have 10/5, right? Right, so we're going to be increasing as we move down, right? So as we go from, as our x at this point starts here and it moves down, we should be getting greater, right? Now, something to keep in mind is that our x doesn't start until we're 2 feet deep. So, for example, right, I want my y distance here to be 0 on that spot, right? And when I'm at that spot, I'm 2 meters down. So instead of 2x, I want to do 2x minus 2, if that makes sense. I'm going to just kind of shift it up a little bit. So instead of starting at 0, I'm going to start at 2. Okay, and then work my way down. Okay, so that is my equation. And notice, right, what should happen? Right, that. So we got that equation now. Notice this is 5 feet, right? So 2 plus 5 is 7. So if I put 7 in there, I should expect to get 10, right? Because I went all the way down. And is that what I get? Do 7 minus 5? 7 minus 2 is 5, and then 5 times 2 is 10. So this is precisely what we want. Okay? We wanted this y value, kind of this y distance, let's change it so that we move up and down. And using that slope there, we found this is going to be our equation we're going to use for that length. Okay? So there's really a lot of thinking that goes into these problems. You need to really just think through, okay, where, what sort of equations can I work with? How does it change as I move downwards? We're going to be left with y equals 2 times x minus 2. Okay, that is the length of this rectangle at each given point. So when x is 2, it should be 0. Whenever x is 3, I should have 2, right? So this should be a length of 2. Whenever x is 4, I should be at a length of 4, etc. Yes.
This is a 2D triangle.
Yeah, it's a 2D triangle. Mm-hmm. Yeah, where the objects we're thinking about right now are just kind of flat plates. We're not worried about their thickness or anything at the time. So, okay, good. So, what is the area of each individual rectangle? Right? It's going to be delta x times y, which y is 2 times x minus 2. So we're going to get 2 times x minus 2 delta x. Okay, good. Fantastic. Any questions on that to this point? Okay. Really, there's just a lot of these questions just require a lot of working through it and kind of thinking about what works. There's not really a straightforward do this and then do this next, right? You just want to find what you want to say. I want to get the length of this rectangle. So what can I get from this object that will give me the length of that rectangle? Well, I have to turn your head sideways, but just see, oh, that's a line. So I can get that. Okay, so we're working with feet, right? Because we're working with feet, I'm going to be using my. Oh, sorry, this should be feet. We're going to be using this delta here. So I have the 62.5, which is good. The area is 2 times x minus 2 times delta x, which I have. Okay. And then we want my distance, right? So again, that distance is going to be how far I am from the surface of the water, right? So again, we're going to use delta 62.5. Now, cubed, if you're curious, should be feet squared. And then, so I want to know how far I am from the surface of the water. So what is d going to be in this case? What should I use to represent that? Right? I just want to know. I want to be able to say I've moved down this x distance. So what is the distance that I've gone if I have gone down x from the surface of the water? X. Just like that. Okay, good. So that's going to be my. Okay, it's just simply just whatever x. Okay, so we have the area, we have our kind of density and our gravity together, and we have our distance. So now we can find the area of this thing, right? So to formally find this area, right? We would, that's the area of the rectangle. So area is going to be, which I'll write this as the integral, but again, it's just good to kind of see it in terms of where it comes from in the Riemann sum. We're going to have the limit as n approaches infinity from I equals 1 to n of this thing. So we're going to have 62.5 times 2 times x minus 2 times delta x, which I'll save, times the distance, which is x, and then all that. I'll just put delta x on here. Okay, but this is precisely what I want for an integral, right? This is my definition of an integral, where I have the limit of a sum, I have some function, and then times delta x. So then I can write this as the integral from. Okay, now we want to be careful here, right? Whatever my bounds of my integral are going to be wherever the shape's at. Okay, so I want to go where the top of the shape's at. I want to go to where the bottom of the shape is at, right? So how far down is the top of the shape? It's 2 feet. Good. How far down is the bottom of the object? 7. Good. So we go from 2 to 7 of 62.5 times 2 times x minus 2 times x. Right? Now, if you simplify this, multiply it out, right? I can even take out the 62.5. Maybe even I'll take out this 2 as well. Why not? 62.5 times 2. 62 times 2 is going to be 124, so 125. Integral from 2 to 7 of x minus 2 times x. So x squared minus 2x. Can I integrate that? Yes, we can. Okay. So what's the integral of x squared? And what's the integral of 2x? 2 to 7. And so that's going to leave us with, so we're going to get 125 times, so we get 7 cubed. So 7 times 7 is 40. Yeah, it's going to be 343. 7 times 7 is 49. 49 times 7 is going to be 343 over 3. Minus 49. And then plug in 2, so we get minus 8/3. And then minus minus the x squared, so plus. And so whatever this ends up being, which I can probably try to work it out real fast. Let's see. 343 minus 8 is, that'd be 335, and it's that 5, 6, 7, 8, 9, 10. It's not 3. That's a shame. Oh well. So 125. Gonna finish this out, right? So we get 335 3 minus 45. 45 times 3 is 135. So 335 minus 135 is just 200. So we get 125, 203, or, and then you just take the, I can leave it like this, so we don't have to calculate. And this is pounds in this case. Okay, so I understand that these are harder ones. I mean, even when I come to these, sometimes we have to like really just kind of sit and work with it a little bit, think about it. But let's walk through what we did again, right? So we said this is what I want to find, the force. So I need all of these things. Rho, I got it. G, I got it. Sometimes they're both together in terms of the 62.5, which was the case since we were in feet here. And then I need the area and I need the depth. The depth is easy. You could always do the depth first if you want. That's just how far you are from the surface of the water, right? Which is going to be x in this case. Now, if for some reason you chose, again, I chose the origin of the surface of the water. If you put it down here for some reason, your depth would be, you have to calculate it a little differently, which you can still do. I think it's just more straightforward to do it from the surface, right? Because you're just doing it from the depth there. And then the area, which the area is going to be the hardest part, right? But one of your components is always going to be delta x. So the hardest part of these problems is figuring out what the other part is going to be. Once you figure out what that part is, then everything runs pretty smoothly. I wrote this step. You don't necessarily have to. You could just skip straight here if you want to. Put in the integral. You're just putting everything you had for this expression into the integral down here and work it out. Okay. So I'm going to do another example. Don't worry. We'll run through another one. But that's the idea. The hardest part here is getting this. Any questions for me right now before I do that? Okay. Let's do another one. So maybe I'll go ahead and I'll write answer for that one down there. So I can have some room here. Okay. So now let's work with this object, right? which is a semicircle. Yeah, so that's a semicircle, which is some of it's on top of the water, but the 4 meters of it is within the water. Okay. Do I know how long this is? What is it? 6. Okay. The reason we know is because we have a semicircle, right? It's a circle, right? So that distance on the bottom is the diameter, right? So the radius is going to be half of that, which means that this is the radius, and that's going to be 6. Okay. So we know this, we know that, and we know this thing, right? So again, for the sake of simplicity, I'm going to make the surface of the water my origin point. Okay, so I'm going to have my origin be here, and we'll have the axis go downwards. Okay, so we're working with meters now, notice. So I do need to, instead of using 62.5, I'm going to be using that 1,000, that 10 number. So I'm going to write those. So rho is 1,000 kilograms per meter cubed, and G is going to be approximately 10. This is a bit approximate as well, but this one's a lot closer. This one is. Again, for G is supposed to be like 9.8, 9.81, but we're going to round to 10 for this ease of calculating, right? And I'll do it now so you don't get confused when it comes to the test where you're supposed to use it. Well, technically it's supposed to be 9.81. Okay, so we have those two things, right? And again, I said my origin is right here, right? So my depth is also going to be expressed by the same thing that it was in the last one, which is going to be. Okay, that's the nice thing about choosing the surface. It's always just going to be x as your depth. The hardest part, of course, is going to be finding the area of each individual rectangle. So let's do it. So okay, so here's how this is going to work out. Okay, because your first instinct, again, just like that last one, might be to try to get the equation of that semicircle, which you can, absolutely. I think that's a great idea. It's still a great idea, right? We just need to be a little more cautious when we're finding our with our origin and everything and figure it out. So this is, again, maybe we'll make our, I don't know, I'll call it left or right. I call it y in our last example. Maybe we'll call it something different to make it a little easier to see. I'm going to clear this out a little bit. Again, here's a rectangle, and the width is delta x. So I want to figure out what the length is going to be. And one thing I know for sure is that if I want to know how long that this length is going to be, so if I have, let's see, we want to use. Okay, so we're going to do. This should do it. I'm going to move my axis real fast. It'll make it see. So we're slightly off. It's a little weird. So that's going to be where my axis is going to be there now. I'm going to do the center. Okay. So now I'm going to name a variable here, and since this is x, just for the sake of simplifying the calculations, I'm going to do. I'll call this direction t. Okay. So what we're going to want, right, is. Right, what in general, right? So let's talk about in general, what is the graph of a circle look like? Just like, you know, if I gave you this graph, right? Just have x and y. What would the graph of that circle be? It'd be y equals what? Yeah, and it depends on the radius, right? You're thinking of the area. I'm wanting what the graph is, not the area. Yeah, so in this case, it could be 1 minus x squared. It could be 4 minus, just it depends on what the radius is. So in general, it's going to look like this. It's going to be r squared minus x squared. Okay. Now we have the radius of this shape, correct? Right. So that's great. The radius is going to be, what's the radius of that circle? 6, right? Because we said it was 12 all the way across, and half of that's going to be 6. So we're going to have the square root of 36 minus, and I said this way is t, so let's say 36 minus t. Okay, so that is going to be my kind of my height in that case. And then since we're using the surface of the water, we also need to consider that I'm 4 meters down, right, from the surface, right? So we need to take that, subtract 4. It's kind of flipped this time. Makes D really easy, but okay. Let's see. So in this case, my positive axis is going this way, so my semicircle is flipped around. So I need that to be negative, and then I'm going to add. I have that 4 distance to it, so I move it up a little bit. Go ahead, you get this. Okay. Now, by all means, it might be easier in this case if you want to set the origin here, because it would make your depth would change a little bit. Maybe I can show you guys that way real fast. So if I put the origin here instead of the bottom of the shape, right? Then what's going to happen in that case is my depth can't just be x, right? Because I'm not going to be x down at that case. So whenever I'm at 0 here, I already have to be 2 down from the surface. So my depth is actually going to be x plus 2 in that. Okay, so this is kind of the first case if we do it that way. Okay, and then we have to kind of work with this. In the second case, I would just have to say d is x plus 2, but that's let's see. That's still we're having to go down. Maybe, well, it doesn't matter much. If it's there, then it won't be a big deal. Like just put a negative on it at that point. But our x is just simply going to be. Oh, sorry, that's 4 in the next list. No, that's not right. Sorry, guys. So if I make this my origin point, right, this is going to be 0, right? But I need this to be a depth of 4 when I'm at 0. But whenever I'm at this point, right, when I'm halfway up, when I'm at 2 meters, I need it to be 2 meters. And when I'm up at the top, when I move 4 away, I need to be, wait, no, it would be 4 minus x if it was going upwards. That's the thing. It really just depends on how you put the axis, right? These problems, the hardest part of these problems is just setting it up in a way that's convenient, right? Because I could have the axis go up. This original arrow here I have was for the radius. But if I have it go down, then it would actually be x plus 4. Because in that case, these would be negative numbers. So it would be 0, and then negative 1 would give you 3, negative 2 would give you 2, negative 3 would give you 1, negative 4 would give you 0. So that is actually And in this case, we get 36 minus d squared. But if you did flip around the axis, then this would be 4 minus x, and this would be constant. The whole, I don't know, let's see. Would you guys prefer to work with this one or work with this one? They're not much different in the scheme of things. But the second one? Okay, that's fine. Let's do that one. So we moved. So now maybe I'll do it with the green line so we really know. Here is our axis. Okay? This is the positive x this way. Okay? The negative x goes upwards. Okay? So the reason that my depth is going to be x plus 4 is because I'm going to have, when I move up 1, that's negative 1, because that's the negative axis, right? So negative 1 plus 4 is 3. Negative 2 would give me 2, and so it's going to work out as it's supposed to. Okay? Let's see. So that one was probably the easiest way to do that one. This one's a little bit of a special case here, just so we make our lives easier. So I'm going to redraw this. That's okay. A lot of thoughts going on here, so hopefully you kind of still benefit in some way as we kind of thought through all this. But I'm going to redraw it, and let's do. So we're going to make this as easy as possible. And then this distance is still 4. This distance is still 12. And we said that the radius is going to be 6. Okay. In this case, D is going to be x is going to be 4 times. Just like that. Okay. Now why? Again, let's talk about it. If my positive axis is up, then my x becomes positive as I move up, right? So when x is 1, I get 3. When x is 2, I get 2. When x is 3, I get 1. When x is 4, I get 0, as expected. That's how I'll keep my own, okay? And then if I go above, I'll be something. Now, again, if I let this be the x and this be t in this case, right? My area, right, or sorry, my x is going to be represented at height. At each case, it's going to be represented by the square root of 36 squared. Okay, why? Well, that's because as I move this far over, right, in the t, I'm within the circle. This is the area of the circle, and the radius is 6. Or sorry, it's the height. Right. So what I'm saying here is that kind of represents the height of this rectangle, but I don't want that ultimately, right? It's nice to kind of know what that height is going to be, because it's going to help me to figure out what I actually want later, right? But again, we're not interested in this rectangle. We're interested in this horizontal one, which has delta x, right? But I do know what the height is at each point, right? So again, let's say that I have this rectangle, and I'm going to put a little one, kind of a little line over here, and just remember to say that this is the square root of 36 minus t squared, depending whatever t I'm at. Okay. Now, this length, if you wanted to know it, is going to be t, right? Just from the middle out. And then this length is going to be like, so we kind of get a triangle form here. This length right here is going to be 6. Okay. Now, the reason being, again, notice we're inside a semicircle still, right? So if I go from the center out to the edge of the circle, that's my radius. That's 6. Okay. So that's going to be that part of the triangle. Okay, fantastic. But I know all the sides of that triangle, right? And so, actually, I didn't even. We had x in terms of t, right? I just need to know what t is. That's going to be my length. Okay. So we're going to have. So let's solve this thing for t, right? Because we want to find how far this is, right? Because ultimately, right, we want the length of the rectangle, right? But in order to get the length of the rectangle, I need to know kind of how long each of the two sides are. So I'm going to take this, I'm going to solve for t. So I'm going to get x squared equals 36 minus t squared, or we get t squared equals 36 minus t squared, or we get t equals 36 minus t. Just like that. Okay, fantastic. So that is the length of this side of the rectangle, right? But there's a whole other side as well, but it's the same length. So what should I do to this t value down here? What do we think? What do we think? Double it. Good. Thank you. I'm glad some people are still following here, so that's great. This does I want us to be able to struggle through it to understand, and not just kind of I'm going to do the perfect answer, and then you can just do that because you're going to run into these issues. So you think through, right? So I'm going to get. So in the end, my area is going to be 2 times the square root of 36 minus x squared. Okay. Now we have every tool we need to put into the integral, so the easy part just comes now, right? So we need to make sure we're capturing all of our shape though, right? So what bound should my integral have, right? So again, this is base. What is it? Positive 6 is correct, not negative 6 though, right? Because negative 6 will technically be down here according to our graph. So we actually need to do 0, right? We're only going from 0 to 6 because that's the top. Okay. You would only get a little bit of it because you still need to factor in. Notice when I go to 6, I'm going to have like a negative portion that's going to kind of cancel it out, kind of like a little Boole effect of some sort. But you need to take all of it into consideration. So, okay, 0 to 6, and we're going to have 1,000, right? Because that's my density times 10 times the area, which is 2 times the square root of 36 minus x squared, and then times minus x. So this is going to give us, and I'll just go ahead and pull this out. This is 10,000 times the integral from 0 to 6. Maybe I'll pull out the 2 as well, because that's just 2. We're going to do on there. So we'll have 20,000. And we're going to get, I'll go and just distribute as well. So we're going to get 4 times the square root of 36 minus x squared minus x. 6 minus x squared. Do u sub for. Say because you can try and do u sub in there, but it would just make it a little strange. But we get to this point, right? In any case, and so we can work with this. Now this one we can do doing a u sub, right? This is totally a u sub problem right here. The issue is this one, right? Which looks hard at first, but in all honesty, this is really easy to find the area, right? Because let's think about it. Again, this is a circle, right? This is just the top half of a circle, right? Times 4. And we're going from 0 to 6. So that's precisely from the middle to this edge. So I want to find the area of this corner of my circle. How do I find the area of a quarter of a circle? What's the area of a whole circle? Pi r squared. So you just do, it's pi r squared over 4, right? And what's r in this case? This guy? 6. So I'm going to get, so this piece right here with the integral is just going to end up becoming pi r squared over 4 times another 4, put in the 6, so we get 36. So a little bit of geometry, you might encounter a problem like that. I think the ones that I gave you should be able to do without, because I know that doing the geometry of it, some people just forget, but it's always a possibility, right? Let's talk about this one though, real fast. So how do I evaluate? So maybe I'll put it here. Just note that minus the integral from 0 to 6 of this. So what do I need to do this one? What do we think? How do I evaluate this integral? I have 36 minus x squared and I have an x. It's not by parts, not partial. What is it? We do a u substitution. 36. Right? Again, let's really try to think through a list of things, right? Do I simplify first? Well, I can't simplify this. Can I use a simple u sub? Absolutely. We're going to let u be 36 minus x squared. So then du is going to be negative 2x dx, but we just want x, so I'm going to write du over negative 2 equals x dx. So here, right, again, that's 36 pi. This is going to be, so we get plus, because we have the minus out here, 1/2 times the integral of the square root of u du. Let's go ahead and change your bounds as well. When I put 0 in, I get 36. Or yeah, when I put 0 in, I get 36. And when I put 6 in, I get 0. Okay. How do I integrate the square root of u? Power rule. Good. So I'm going to rewrite it and shoot to the 1/2. So we're going to do 1/2. And then when I integrate this, I'm going to get 2/3 u to the 3/2. And then from 0 to 36. 0 doesn't give us anything, or sorry, from 36 to 0. 0 doesn't give us anything, 36 does. We're going to have 1/3 times 36 to the 3/2 minus. How do I do 36 to the 3/2 power? Take the square root. Good. So what's the square root of 36? 6. Thank you. And what's 6 cubed? 216, right? So we get minus 216 over 3. So that's that value. So in the end, after all of this, our final answer is going to be 20,000 times 36 pi minus, so the 1/2 cancel it out with the 2/3, so we get minus 1/3 minus 216. 3. Okay. So let me reiterate by saying any of the choices that I made for this problem would have worked completely, right? The only reason why I ended up going with this one is so that my integration bounds would have all been positive, right? Because otherwise you would have had negatives, or you would have made your equation here a bit more complicated, right? Let's kind of go over real quick again. I won't take too long in this because I just got to move on to the thing, but anytime you're dealing with that circle here, right? And you want to find what the length is at any point, right? The thing to keep in mind is, right, so I want this rectangle, right? So you can kind of do what I did and like get the height and then just solve it in terms of the other one. Or we can always just recognize this as a triangle here, right? So where I have this, where I get t, right? This is kind of my t distance out, however far it is. This is 6. And then this is going to be my whatever x is supposed to be. Or sorry, yeah, that's whatever the x value is, right? Because that's how far up and down we are. That's the x direction, right? So after constructing this triangle, which we know Pythagorean theorem, we know that x squared plus t squared equals 6, which if we're solving for the length here, we get t is going to be the square root of. And that's where that ultimately came from, right? So triangles are very important. Use them. It's going to help. I assigned a few of these on, I think I made one on the mandatory one, but I assigned a few of the extra, so I'll just encourage you to practice them. And I'm happy to try to be there as well to help you think through it. I understand that they can be. Okay. Is there anything that's there now that I can try to clarify a little more for anybody involved? Again, I know it's not the easiest thing. Honestly, I was messing up a little bit. Yes.
When you were making what were the other options?
So, yeah, there's like 3. I mean, you could always do a lot of options, but the 3 main contenders I had in mind were do the surface of the water, right? So I would put my my horizontal axis there, or I would do it, I guess my 2 in this case, or I would do it here, right? Or I either do it at the surface of the water, or I do it at the surface of the shape, right? Now, in the case of the triangle, it was easy to just do the surface of the water, right? Because the shape was just a triangle, so you're just working with a linear equation. However, in the case of my circle, the original idea was, oh, let's just make the depth easy to do. But it ultimately made finding the area of the semicircle, like at each point, a little harder to do, right? Because then you had to worry about the factor being added in, and etc. Right? But then you also have to think about, do I want my axis to go down or up? I could have finished this problem by just having the axis go down, but the bounds I would have been plugging in would be negative here, and so it was just for the sake of making this easier, right? Kind of visually, instead of like, oh, we're only doing negative numbers, what's going on there. So sometimes it might be easier to go upwards, right? It's all about kind of experimentation, right? But whatever you end up doing, make sure you're consistent with that throughout. Make sure that everything you're doing makes sense, right? Because if you say, if you chose this one, right, the one that's here where the positive axis goes up, and you said, okay, well, d should be 4 plus x then. That's not going to make any sense because your positive axis is going up. So what you're telling me is that whenever you're one spot up from the bottom of the sphere, then you are 5 meters deep in the water. But that's not true, right? This is supposed to be 4. So if I move up 1, I'm supposed to be 3. But if you use this as your depth, you put 1 in there, right? You go up, and you're going to get 5, right? So it's all you really need to just be careful, right? Just make sure your numbers make sense. Okay? Yes.
Question. Where did you get that 36 pi on the integral? You were like solving it.
Oh, right here.
Yeah. So that.
So again, this is one that we could do doing trig sum. Absolutely, that's fine. To work it out. What I did is I just used the geometry argument for it, right? Because that's a circle. So what I said was, okay, let me draw that circle out. I'm going from 0 to 6. So I just need a quarter of the circle. The area of a circle is pi r squared. So the area of the whole circle would be 36, right? But I only want a quarter of it, so I divide that by 4. So I would get 9, right? But there's a 4 there, so it just kind of cancels each other out. Okay. So then I end up with 36 pi anyway. Yeah.
I'm not sure if it's explained it at the beginning. This equation works because you're adding the density and the gravitational constant part of the shape. So
yeah,
when you took in the second example how to solve the problem, the surface level of the water wasn't accounted for. feel it shouldn't go through, is that not that what you're talking about?
Yeah, the surface of the water does not matter for the area. Right, because the area is not dependent on, now, obviously, depending on where you put your origin, that might affect the area. But the water itself doesn't affect the area of the object. The area is independent.
Assume there's like no tether to it.
So, yeah, the area, you don't like, I mean, the water might give you an idea of where to put your axis, right? But, yeah, that doesn't need to be the area. But if you do choose your origin to be a certain height, you know, pretty low or pretty high from where the shape is, then you just need to be careful. Okay. There's a couple of examples. The book gives more as well. Obviously, I wanted to do these ones along with the one that the book gives, so you really know the full picture of it. And they kind of lay it out for you. So hopefully it kind of makes sense. Okay. So that's the hard part of today. Everything else is easy. Okay. So let's go ahead. We'll do the second part here of this section. Which I'll just try to like kind of explain real quick. Maybe I'll do one example. Okay, any last questions on this? I do want to apologize just for if I did confuse you on the way. The thing is, there are a lot of ways to do it. So I was trying to find the easiest way, but ended up getting. Now, after all of that, in terms of the hydrostatic pressure, we move on to the second part of this section, which is just talking about moments and centers of mass. Okay, so I don't know if you've ever worked with moments before at any point. We're talking about like the center of mass at any time, but it's just. It first just talks about, right, if I have a rod, right, with a weight here and a weight here, right? And I want to, and maybe they're not equal, oftentimes they aren't equal, right? I want to try to figure out where would be the right place to put the kind of the fulcrum essentially of this hat so it stays perfectly balanced, right? And the way that we figure this sort of question out is we appeal to moments, which we get moments by looking at what happens when I take the distance I am away from kind of my center point and then multiply that by the weight or the mass at that point, right? So, for example, right, if I have, let's say that this is 4 kilograms and this is 8, right? And I want to figure out, where to put this at to make this work. Then what needs to happen is I need to fix this. Because I need this distance to be 4. And I need this distance to be 8. Now why is that? Well, that's because I need whatever's happening on this side to be equal to what's happening on this side, right? Notice if I take 8 times 4 over here, 4 times 8 over here, I get the same thing, right? But they're pulling each other slightly different. But what's happening is that the moment on this side is equal to the moment on this side still, right? Because this is a smaller weight. Let me fix my picture real fast. There. 4 and 1. Oh wait, no, those. we want to happen is we want these both to balance out, okay? So in general, right, we would label like these points, kind of our mass points, so I call this one M1 and M2. And then this is my first, my D1, and this is D2. So in all cases, I need M1 D1 to be equal to M2 D2 in this case, right? Because if it's not, right, then it's going to be off balance. It's going to kind of fall over. It's going to slip. It's not going to be balanced enough. But in this case, at this very moment, it's going to be perfectly balanced, right? And this discussion doesn't just, stick to these rods, but we can go further, and we can talk about like points in a plane, right? So if I have the point 2, 1, for example. -1, -1, and we'll do point 2 or -2. Right. I want to find a point in the middle of each of these, and each of these might be given a certain amount of weight, right? Like that this point is going to be the most significant one, so I'm gonna let it have a value of 8. And this one's kind of like a close behind, but not quite. So I'll give it 4, or maybe we'll give it 6. And then this -2, 3 really is unimportant, so we'll have 2. But it has this weight, this has a weight of 6, this has a weight of 8, right? And so I want to understand if I have these 3 points happening, or 4, I want to understand what the center is to kind of balance all those out based on the distribution of the weight, based on how we figure, what happens when we take all these into consideration. And the thing that we have to do is we have to find, like I said, this thing called moment, which in this case, the moments were, pretty simple because it was just you have this side and you have this side. But now, since we're having more directions, things are going to be a little more complicated, right? So there's going to be 2 different moments. There's one moment that goes in the y direction. And this moment is going to be characterized by some one goes to n, right? Depending on how many points you have, of mi. Next slide. Now you might have expected to be a yi be there, but that's not the case. We don't want yi. We want we're going to know the moment in the y direction, right? So I say, okay, right, for each of these pieces, I'm saying, okay, how far away from the center am I, right, or how far from my center point, and then how much mass is on there, because depending, that's going to tell me how much that specific piece is going to pull me in the y direction, right, kind of pull me in that y direction, right, kind of think of this shape again, right, if I go out 4 and this weight's 8, it's going to affect me different than if I was out 16 and it was 8, right, because this can maintain a little better because it's close, but if this gets way farther out, it's going to be hard to control that, okay? So that's we're talking about the up and down movement, which is the x, right? But in accordance, we also have a moment in the x direction, depending on the y. Like this, right? So if I ultimately, I add all these up, right? And what this is going to tell me is this is going to reveal to me what the center of the system is going to be, right? Just like here, where I can figure out where the middle needs to be, so these equations work out. I can use these formulas to help me perfectly find a point that's going to be balanced between these 3, right? And the way that we do that is I take my moments, right? So for the x point, right? Because we want to find a point ultimately. So to get the x point in this situation, I'm going to take the moment in the y direction, and I'm going to divide that by dm. which is the total mass in this case. Okay, the total mass. To find y bar, which is the center, I'm going to take the total. I'm going to take the moment in the x direction, and I'm going to divide that by the total mass. Okay, because, right, we kind of saw the mass being distributed differently depending on where each point was, but we're going to take that mass as a whole to determine ultimately where the center is going to be, right? So let's take the example we have here and try to see does this work out accurately as we expect, right? So I'm going to have, so let's find my first. So I'm going to have the sum from I equals 1, and we just have 3 points, right? To 3. Okay. And so, which is going to be, so we're going to have mi xi. It doesn't matter which one we choose to be xi. It's just, you just kind of pick each one as we go. So I'll start, this is the first point I made. So mi in that case is going to be 8. And then xi is, what's the x in that case? The x value, we're talking about from the origin here? 2. Okay. Now, so now we'll do maybe the 6th point, because that was an x, so 6. The x point in that case is -1, right? And then the last one was 2, and that point was -2. Okay? Is that the mass of that point was 2? So we get 16 minus 6 minus 4, which is going to be 6. Yes. Okay, great. I'll find mx as well. So same thing, we use the formula, but put y's in instead. So I'm going to have 8 times 1 plus 6 times -1 plus 2 times 3. Right? So we're going to get 8 minus 6 plus 6. 8. Okay, now to get my points, I take, so x bar is going to be my divided by the total. So what is the total of the 3 numbers there? 2 plus 8 plus 6, what is that? 16. Good. So we're going to take 6 over 16, which is going to give us 3 over 8. So that is my center of my x. So that's going to be probably about here somewhere. Let's do y bar. And so that's going to be the center, the mx, which is, so mx over m. So we get 8 over 16, which is simply 1/2. So we go to 3/8 and we go up to 1/2. And so that's going to be okay. So does that make sense? Does that look appropriate? Does that look like the center of those 3 points? Yeah, it does. I mean, you may have moved it over slightly, but it's definitely, its pull is mostly towards this one, which makes sense because that's the one with the most weight. It's still not too far from here, and we would expect that would be the farthest from this guy, which my picture may just not be the best in this case. But. Okay, good. So there's that, right? But we're going to take this. That's x equals y over m. Okay, so why are we talking about all this? Well, because let's talk about this section of the book, but also we're not just interested in points. We want to know the center of like actual objects. So let's call it centroid. Okay, so we're going to take this and we're going to apply it broader, right? To where I have a function like f of x. Right? Here's my right? Here's my solid essentially. And I want to figure out what the center of this object is going to be, right? So where it, as long as it's kind of evenly distributed in terms of its density, where's my center of mass going to be, right? Where's going to be the point that if you kind of sat it on something, it would be perfectly balanced, right? We're going to find the balance point in all of this, okay? Now, this doesn't look like something that's going to be very easy to find. You think because we're not just dealing with points anymore, our equations may not work as well, but we still can, right? And the key thing is I mean, we know how to work with three-dimensional sums and how to do things as we approach infinity, right? Because there's really an infinite number of points here, but we can still work with it. So, guess what? Again, we're going to take this, we're going to break it into rectangles. Okay, but I'm going to take it to break into rectangles. Now, can I take a rectangle in isolation, right? And find the center of that rectangle easily? Can I find the center of this rectangle? Where's the center of this rectangle? It's gonna be right here, right? It's gonna be halfway this way, and it's gonna be halfway this way, right? Which, so that, this is kind of like this point here is kind of going to be your X bar in a way. It's going to be that middle point. And then this is going to be or X I bar. What the X's are. And then this is going to be half of whatever X I bar is, right? We want to, similar to when we did the midpoint rule, we kind of want to use the midpoints as our guides here to make these rectangles. And so since the height of the rectangle is going to be half of xi bar, we're going to have that to get to the center. Okay, now if that's the center of that rectangle, right, I can just take that, add up all these pieces together to get me a total, right? So first thing, right, let's say that my object has a density of a row. So density is row, right? We don't know what it is. It doesn't really matter, but we want to have that density, right? So that's going to be like per meter squared per area. So that's just how much, I guess, material is there in each case, right? So to find the mass, right? Because again, we had a mass here in each case. We said they're kind of unitless here, and it'll be the same. But we need to get the mass of each of these rectangles, right? So to do that, right? Again, this is in this units, or the units of this row are generally in terms of whatever kind of the mass unit, if it's kilograms or if it's pound mass, whatever it is. I need to get the mass. I need to take row. In my case, the area of each of these rectangles is simply just f of x. Area is going to be f of xi bar. So that's going to be my area, right? So my mass of each of these rectangles, so I'll say mr maybe, is going to be rho times f of xi bar times delta x. Okay. How does that help us? Well, we can find that for this specific rectangle, right? Since we know the center already, we can easily find what the moment of. We can kind of take the center of that rectangle in general to give us a general moment from this rectangle in terms of my whole shape. And the reason is because, well, here's my axis, right? So if I want, instead of having to do all the points in the rectangle, if I already know the center of it, the moment is just going to be dependent on how far I go in the x direction to get there and how far in the y direction I go to get there, right? So the moment So I'll write for MYI, basically for my rectangle. I'm going to take rho times f of xi bar times delta x times the distance from my origin point to that rectangle, right? So let's say it's this rectangle. Well, that would just be the same xi bar. So I take this and multiply it by xi. Okay. Similarly, to get to this rectangle, to get mxi, I'm going to take rho times f of xi bar times delta x times whatever the height is up to that, which we already discussed is going to be 1/2 f of xi bar squared. Or sorry, not squared. Got ahead of myself. Okay, so that's the moment of each rectangle, right? And that's just because we know what the center of the rectangle is already, so it just cuts off a lot of work for us. Okay. Coming over here. Again, as always, right? We need to do the sum, right, of these. I want to do the sum of each rectangle in order to give me the ultimate moment. So I need to take, so this is just m and y in general, is going to be the sum from I equals 1 goes to n of, and of course, we're wanting to find the moment for this kind of continuous function. So we're not just want to stick with approximations, so we're going to take the limit of as n approaches infinity of the sum from I equals 1 goes to n of, we're going to have rho times f of xi bar times xi bar delta x and mx, the limit as n approaches infinity of sum from I in a row times, now I want to take the f xi's there and just multiply them together. So I get 1/2 f of xi squared times delta x. Okay, but this is an integral, right? Or with the limit, right? This is a Riemann sum because we have our function and we have the delta x. So this is going to be the integral from, and we're just going, all of our rectangles are going from one end to the other here. So whatever a and b is going to be our bounds. And we're going to have rho times f of x, x now again as we go towards infinity, times x, replacing that xi bar, double dx. Okay, and similarly here, we're going to get the integral from a to b of rho times 1/2 f of x squared dx. Good. So we get that. Now, let's think about the mass of our object, right? Because we said to get the centroid in the kind of 3-point case, we took the moments and divided by the mass, right? Well, the mass of the object, again, is just the density times the area. And we did that for the rectangle in specific, but we can do that just for the whole shape as well, right? The mass, again, is rho times the area, but the area underneath the curve, we've been doing so much, right? That's just the typical integral. We're going to have rho times the integral from a to b. Next dx. So what this means in the end of everything is that x bar equals my over little m, right? Moment about the y direction over my mass, which is going to be the integral from a to b, and I'll go and pull up this row here, of x times f of x dx over rho times the integral from a to b of f of x dx. But the rows are going to cancel, they don't matter. We get the integral from a to b of x f of x dx over the integral from a to b. Okay, now I'm going to write this last one. We're going to have y is mx over m, which is rho times the integral from a to b of 1/2 f of x squared dx over rho integral dx. Let the rows cancel yet again, leaving us with the integral from a to b of 1/2, which that 1/2 can come out as well if you want, but it doesn't have to. Fx squared dx over the integral from a to b of fx. Good. So if I want the centroid of this, I just have to evaluate two integrals and divide them, right? I do x times f of x for the x, and then I do 1/2 f of x squared. Okay. Now, keep in mind, and I know some people might be thinking to just divide the f of x's. You can't do that. They're inside the integral. Okay, we can divide the rows because they're constants, but we can't divide the f of x's. So you have to evaluate each integral. But you could just do this one once, and then just evaluate each of these separately. Okay. Yeah.
Spell the.
So yeah.
Is there a section on this in the textbook or is
This is in 8.3. Okay. Yeah. It's just the second part of 8.3. This is called a centroid. This is the centroid of my area, whatever it is. Okay. So let's just do an example. We're going to do and this is number 26. So I want to find the centroid of this region. Great. Okay. So again, the region we're talking about in this case is going to be this section. Great. And so I want to find the centroid of this. So I'm going to take. We need to do both of these, right? Just do x bar and do y bar, right? So we're going to do 3 different integrals and we'll put them together. So first, let's do the integral from 0 to 4, right? Because that's going to be our bounds in this case of f of x dx. Can I do this integral? I would hope so. This is going to be, again, we want to write that as x to the 1/2. So we get 3/2 over x to the 3/2 over 3/2, or 2/3. 0 to 4. 0 doesn't give us anything. 4 to the 3/2. I take this square root of 4, which is 2, and then we do 2 cubed, which is 8. So we get 2 cubed. 2 over 3. That's right. Okay, so that one's not. That's not right. 2. We need to find the integral from 0 to 4 of x times the square root of x dx. What do we think about this one? What should I do here? Good. So I can write this as x to the 1/2, and this is x to the first power. So I can do what with the powers? It's going to be x to the 3/2. Good. So we're going to get the integral from 0 to 4 of x to the 3/2 dx, which I can integrate. I get x to the 5/2 over 5/2, right? Just add 1 to the power. So we get 2/5 x to the 5/2, 0 to 4. Which 4, when I put it in, you do the square root of 2, which is 2 to the 5th power is 32. So we end up getting 64. And don't need to labor on that one too much. I would hope that goes through. We get 64 fifths. 3. We need to evaluate the integral from 0 to 4 of the square root of x. 1/2 times the square root of x squared dx. Okay. What's the square root of x squared? X. So we're just doing 1/2 times the integral from 0 to 4 of x dx. And what's the integral of x dx? So altogether, 1/2 and 1/2, I get 1/4. X squared from 0 to 4. Again, 0 doesn't do anything. 4 squared is 16, and 16 over 4 is. Okay, good. So now we just find both our values, which x bar, or centroid, x bar is going to be 2, right? The second one we found over the first one. So we just take 64 fifths over 16 thirds, which is 64 fifths times 3/16, which is going to give us, so 64 divided by 16, can we do that?
Yeah.
What's that? 4. 4 times 3 is 12. 12 divided by 5 is 5. But it's just 12. Okay, so so x bar is 12 fifths. Y bar is going to be when I take the third one we did over the first one. So we're going to take 4 over 16 over 3, which is 4 over 1 times 3 over 16, which is just going to leave us with 3. Okay, so if we wanted to kind of see it on the picture, just to kind of judge it, 2, 3, 12 fifths. That's going to be a little over 2. So we're going to be here in 3/4. Let's see, that's going to be about 2 right here. So this is about 1. 3/4. Which looks pretty good. That's okay. That's okay. Yes.
When we put our answer, how do you want us to put it? Like just in words?
Yeah, if you gave me that, that's fine. Maybe the best way would be like this.
Okay.
We just kind of write it as coordinate pairs, but as long as I can see where you put x bar and y bar, then I'm like you didn't just write down numbers like you said. Oh, this is x bar, this is y bar, and here's the word to get to it. Okay, cool. So that's it for that. There's a theorem at the end, which I'm not going to worry about covering, and then there's rules for what happens when you're in, like, if instead of just one curve, I'm in between 2 of them, right? And in that case, you're going to follow. You can look at the book. I'll write them as you guys go to leave, though. If you want. They're going to be similar to like the ones you did for volume when you found them, but you just have to do like f of x minus g of x. Okay, good. Go take a break. Yeah. Okay. I'll write those on here. It should be. Yes. Yeah, absolutely.
On the one with the we just multiply the 4 next steps.
Uh-huh.
So when you took the example of that, how did you know?
Right. Well, this one didn't have the X on it, right? So I was forced to say, okay, well, I need to, is there? I was just like, oh, it's by itself, but I know it's a circle. The other one, since it had the X, what I would want to see is, oh, it's U sub, right? It's gotta be U substitution because there's an X with some X squared on the outside, right? Again, if you wanted to, you could have done that one doing trig sub, but
Okay.
you could, I just, also, it was just easier to be like, oh, well, it's a circle, so we can just use geometry.
Okay, so like. Part of it, right? So you said like that was like there. If you decided that you could just do like geometry.
Yeah, and
That's
it's,
like kind of like
and since they're adding and subtracting, I can always just take the integrals, to like split it up, so I can do the integral of this part and the integral of this part. Whether I do them the same way,
that. Okay.
it doesn't matter,
Okay.
right? Because I could split it up and I could do trig sub on this piece and do a U sub on this piece, right? It's just like if I have, you know, I think one of on the first test I had, something like this, right? This one you could just do, you know, it's X squared, right? This one, you might have had to do U sub, but you're not gonna be like, oh, well, if I U sub this, I'm gonna U sub this as well. You could just do them separately, and that's the same thought.
Okay.
I just said, can I do them separately?
Okay.
No. Okay. That's just if you're between two functions. So it says find the centroid between sine and cosine between this point and this point, then you would want to use these. But obviously, if it's just like this one where it's just the function itself, then you can just use the base.
Which figure is that or equation number in the text?
That is. What's the book still? Give me 1 second, I'll tell you. Number, so it's in 8.3, it's number 9.
It's all there.
Hmm?
The left
Yes. I'm not sure if they say A specifically. That's why I put it on there, but A is assumed